This is the second section in the Production Separator Principles module. Section 2 will cover the various types of separators in the field, including two-phase vertical, two-phase horizontal, two-tube horizontal, spherical, three-phase vertical, and also some other three-phase methods. Remember from the last section, you learned that separators can be vertical, horizontal, or spherical. Each type always has 4 sections in common: primary separation, secondary separation, liquid accumulation, and mist extraction. These separators can be classed as 2- or 3-phase depending on the requirements of the particular well stream mixture. A 2-phase vertical separator, like this one, is best suited for well streams with high liquid content and low gas volume. 2-phase vertical separators are typically used when the well stream contains large quantities of mud and sand. Easy cleaning and draining make it best for these applications. Here the well stream enters the vessel near the midpoint of the side. Baffles change the direction and velocity of flow. It is this change in direction which decreases the fluid speed, but the gases tend to flow in the changed direction and move upward. Since liquids change direction less freely than gas, they move downward due to gravity. As the gases move upward through the mist extractor, droplets are extracted by the rings or mesh pad. The liquid droplets form, becoming larger and larger until their weight causes them to fall back into the accumulation section. The gas exits the separator through the gas outlet at the top. As the liquid level in the bottom rises, the liquid level control valve opens, releasing liquid through the liquid outlet. Our next separator example is very similar to this one, except the cylinder has been positioned horizontally. So let's go take a look at it. This horizontal placement increases the liquid surface area, which, in turn, increases the efficiency of the vessel for gas removal. That's why these 2-phase horizontal separators are used for processing well streams with large volumes of gas. This horizontal separator contains a primary separation section near the inlet. Secondary separation and mist extraction sections are in the top portion of the cylinder, and like other types, the liquids accumulate in the bottom. As the well stream enters the vessel, it strikes a baffle. Forward motion temporarily stops, causing the heavier liquids to fall to the bottom. Gas and liquid spray flow along the top, passing through straightening vanes. Liquid drops form on the vanes, increasing in size until they eventually roll off the vanes and fall into the accumulation section. The vanes also straighten the flow of gas. As the gas passes through the mist extractor, the remaining liquid droplets are removed by the mesh pad. The gas exits through the gas outlet. Liquids collecting in the bottom are separated from the gas flow by divider plates. Accumulating solids are periodically removed by washing or flushing through the drain. The liquid level rises until a preset level is reached. At that time, the liquid level controller opens the liquid level control valve, dumping the liquids through the liquid outlet. That sounds simple enough, right? Well, what do you do if your well stream has slugs and surges? You need a separator with better separation to prevent re-entrainment. In our next example, things get a little more complicated. Well, as you can see, we've added another horizontal cylinder. This gives us added separation required by applications where the well stream surges often. The upper tube houses the gas separation section, and the lower tube houses the liquid accumulation section. The 2 cylinders are connected through vertical pipes called downcomers. This separation minimizes the risk of re-entrainment. In the upper tube, the gas separation section contains the inlet, baffles, straightening vanes, and mist extractor. On the very top, you'll see the relief valve or rupture disc. As the well stream enters the top tube through the inlet, the stream is deflected to change direction and velocity. Fluids fall to the bottom of this upper tube, while gas and vapors flow through straightening vanes. These vanes also remove some droplets as they collect on the surface. The gas passes over a vertical deflection plate and then through the mist extractor, where additional droplets are removed. The gas exits the top cylinder through the gas outlet. The vertical pipes, or downcomers, extend into the bottom cylinder below the surface of the liquids there. Liquid which collects on the bottom of the top cylinder flows down through the downcomers into the lower cylinder. Here, sand and other solids settle to the bottom of the cylinder. Under control of the liquid level controller, liquid leaves the bottom tube through the liquid outlet. Two-tube separators can also function as three-phase separators. In this case, gas exits from the upper cylinder. Oil exits from the top of the lower cylinder, and water, being heavier than oil, exits from the bottom of the lower cylinder. All right, I told you earlier that production separators can also be spherical in shape. Let's have a look at one now. Well, this separator is quite a bit smaller than the cylindrical type, and it is this compactness which is the spherical separator's best feature. It provides good gas separation and liquid handling in a limited space. However, when the well stream contains excess mud or sand or is subject to surging or foamy components, the spherical separator is not economical. Now, in this design, the four separator sections are all contained within the sphere. In this top part, 3 sections for liquid gas separation, and in the lower part, the liquid accumulation section. The well stream enters the vessel at the top. Once inside, the stream is deflected to the surfaces of the sphere along the walls over a dome covering the mist extractor. As the stream enters the lower portion of the sphere, the gas and liquid vapors begin to rise, passing through the mist extractor. Liquid droplets collect and fall downward. Gas leaves the vessel through a vertical pipe above the mist extractor. Notice, unlike the other separators we've discussed, the gas outlet in the spherical separators is at the bottom of the sphere. While liquids accumulate in the bottom of the sphere, gravity settling causes solids and some water to collect at the bottom of the vessel. Liquid leaves the vessel near the bottom of the sphere, controlled by the liquid level controller. Spherical separators offer advantages of compact size and good gas handling. In our next category, we'll examine three-phase vertical separators. The three-phase vertical separator has construction similar to the two-phase vertical we examined earlier. The major difference is in the liquid accumulation section. Here, the top portion of the accumulation section collects oil, and the bottom portion collects water. Both areas have their own liquid level controllers and liquid level control valves. The well stream enters the vessel in the upper portion. Stream direction and velocity are changed by baffles. As the gas and liquid vapors rise, baffles or straightening vanes and a mist extractor remove the liquid droplets. Gas leaves the separator near the top. Oil and water fall to the accumulation section, where the gravity separates the oil from the water. Since the settling time is longer than gas-oil separation, the liquid must remain in this section longer than in two-phase separators. This requires a larger liquid accumulation section. The oil leaves the vessel through a liquid level control valve in the oil portion of the accumulation section. Water leaves the separator through a different liquid level control valve. Both the oil and water valves have liquid level controllers. Liquid level control is critical in three-phase separation. The oil-water interphase must be contained within ranges or the oil dump valve will begin to dump water rather than oil. On the other hand, a malfunctioning liquid level controller or valve on the water section could cause both water and oil to be dumped into the wastewater. Three-phase separators may be vertical, horizontal, or spherical. Sometimes the liquid level is controlled by either one or two weirs. A weir is a dam-like structure designed to keep liquids at a given level. In a separator with one weir, the weir maintains the combined liquid level. However, both the water and oil levels are maintained through individual liquid level controllers and valves. With two weirs, one maintains the oil level and the other the water level. Each liquid is dumped by its individual liquid level controller and valve. In this section, we discussed the various types of separators in the field today, including two-phase vertical, two-phase horizontal, two-tube horizontal, spherical, and three-phase vertical. We also looked briefly at some other three-phase methods. Now, it's important to remember that liquid levels must be accurately monitored and maintained by controllers and valves for the separator to efficiently do its job.